So the node structure of a radix tree is you have only one kind of node. That is very useful property. Each node has a prefix, which is, the data structure is generic in that you can have a type class, and if you implement the type class, you can have different kinds of keys. But for this talk, I'm going to concentrate on strings. So the prefix is basically a string. You have a number of children, which can be 0 or more, and you have an optional value. And if you use the data structure as a set, basically the value is of type unit, and it just signals that there's a value at that node. And like I said, there's only one type of node, which is good for JIT compilation because there's no virtual method inlining limits. If you have many different cases, then the JVM kind of gives up on inlining. So this is how the, this is a bit short, but this is how the class is defined. It's final actually, but it took it off so it would fit. And you have a prefix and children and a value. What you might note here is that I'm using type classes, but I don't put the type classes on the constructor of the class, but on the methods. I'll get to that later maybe. And it extends no equals. And this is how, for example, the method to check for, to get an element is implemented. As you can see, I require the key type class on the value, on the method, not on the constructor of the class. It has some disadvantages, but also some big advantages. Most notably, not every node has to have this pointer to the type class. I'm not sure if you heard about this great new development in the Scala world. Scala is going to move to all German identifiers. And since German words are especially good, well suited for showing the benefits of a radix tree, I'm going to use these identifiers as an example. So we all can get familiar with it. So in a year or two, when Scala gets rolled out, we can continue working.
How do you guys use Twitter?
Okay. And I was also informed that it would be helpful to have animated GIFs in my talk, so I decided to have an animated GIF of all keywords starting with a V. And so this is basically how a radix tree works. You always have, when you have several strings, you take the common prefix and put it into a node. And whenever you add a new node, you basically just have to split sometimes on the path. So these are all the very nice German words starting with V. Is looping, as I was informed that GIFs should do. And yeah, you can see basically how it works. One thing to note is that the leaves here are actual nodes containing the value, not values. So if you would show it correctly, then each leaf would have another pointer to a string. But I decided to omit that in order to make it more compact. So why am I using that at all? Why I'm not using a sorted map? It has high performance. Performance is crap mostly, but for some operations, performance is very high. These two operations that I'm interested in is filter by prefix. So you want all keys that start with a certain prefix, like all names with A, and prepend a prefix. So you have a bunch of names, and you want to prepend a letter sequence to all of them at the same time. And as I said, it's generic with an asterisk. And most Java radix tree libraries only work for strings, so they are not generic, which is, of course, because they don't have type classes. And doing it other way would be very inconvenient. So, and I also needed, for one use case, the ability to work with raw Java arrays, because if you want to store a blob and you don't care about immutability, the most compact representation is an array of bytes. There's just no way around it on JVM. So design goals. As I said, it should have efficient prepend prefix and filter prefix. It should be immutable, from the outside. It should be type class friendly, meaning that it should be easy to define type classes for it, and it should come with some built-in type classes. And of course, I'm using the cats and algebra type classes. And it should provide some type classes like EQ, for example. And like I said, it should provide operations that simplify implementing type classes. And I got to focus on bulk operations, which means, I'll get to that later, and I got very fast structural equality. So non-goals are integration with Scala collections. So this is basically a bare data structure that I just need for my own stuff. I don't want to have a comprehensive API. I just implement exactly what I need myself and nothing more. I don't want to have covariance of value type. I tried to implement it, and it was a lot of work, and I noticed that I never use it anyway, so I just threw it out again. And I don't care about nice usage for sets and maps. So if you want to, the thing is a map, and if you want a set, you just have to use unit as a value type. This is unlike Scala collection immutable hash set and hash map, which are basically the same data structure copied, so one looks like a set and the other one looks like a map. And purity of the implementation is also not my concern. Inside I'm using all the dirty tricks like arrays and mutability and null, but you won't get them from the outside. And encapsulation is also not my concern. I just want to make this so that I can use it, and if somebody else uses it in the wrong way, then too bad. My initial use case was the following. I'm again using the nice keywords from Scala. So I had a bunch of identifiers in different local contexts and want to map them into a global namespace with different prefixes. So, for example, I got this set of words, which are German words, and I got this set of words, which are English words, the identifiers val, var, and def. And now, if I have a prefix tree, I can basically merge these two trees into a common tree with this operation. And you get this. And the good thing is that because of structural sharing, you can still use the local tree, so you can still use just the DE tree or the .en tree, but you can also use the whole thing and map all these identifiers in a global namespace. That was kind of my basic use case when I started writing that. And you can't really do that correctly with a sorted map or something, because you would have to replace every key with the string which has a prefix, and you would have to make a complete copy of the tree. So how does construction work of such a tree? There's a method to create a singleton node, which means you take a string and the value, or the key and the value, and no children, done. Or you have next thing is you have a merge operation. That merge operation can take two arbitrary trees and merge them in an efficient way. So, for example, if the two trees don't have any common prefix, the merge will be just adding a single node on top of both of them, because they're completely separate. Yes, like I said, I care about object allocations, so I count them. And then there's a method prefix, which allows you to take an existing tree and add a prefix to all keys. So this might be is a bit different than in Scala collections. Scala collections are implemented, all collection operations are implemented mostly in terms of collection element operations. So if you merge two sets, it's usually done by just taking an element and adding it to the set, and then taking all elements from the second set and adding them to the first set. But that is inefficient, especially in my case. So basically I implemented adding a single element is just creating a singleton and then calling merge. I don't care for that. I like merge, and the single element operation is something that I don't care very much about. But it's still reasonably fast. So was it worth it? I get a test data set is 10,000 German words. I'm using German words because they're nice and long. And here I got basically a comparison. So creation is a little bit faster, but nothing to write home about. Filter prefix, that is the operation I really care about, is quite a bit faster. These are nanoseconds on the right-hand side, which is kind of clear, because if you want to filter by prefix, you just go into the tree until you see the right subtree, then you take that subtree out, and like add the prefix again, and yeah, done. So it's much more efficient than having a collection and then filtering all keys and creating a new collection, obviously. So equals is also quite a bit faster. We'll get to that later. So for my use case, this was totally worth it. For you, it might vary, but for me, it was worth it. And well, as I said, I decided to put it on GitHub just for my own convenience. So one thing that is very nice about radix trees is they got a unique representation, which means a radix tree that has the same keys will always have the same structure, exactly the same structure. This is extremely useful for various things. It allows you to compare two trees structurally instead of basically just checking that all elements are in the other tree, which makes equality faster. And it also enables some tricks I won't talk about now, which is kind of basically assigning some kind of summary to subtrees and keeping those. So as an example of a data structure that is very commonly used, that is where this is not the case, this is a sorted set from scalar collections. And a sorted set from scalar collections is based on a tree set, and a tree set in turn is based on a red-black tree. And for a red-black tree, I mean, a red-black tree has certain invariants, like the number of red and black nodes and so on. So it won't ever degenerate to a list. But nevertheless, there's some variation. So this is the sorted set for A, B, C, D. Now this is, whoops, one too far. This is sorted set for the same strings but reversed. And as you can see, it is, if you put them side by side, you get a different structure. So a red-black tree kind of remembers the history in which you add the elements to a certain degree. So you cannot compare those two structurally. If you would compare them structurally, it would return false, but obviously they are meant to be the same set, because in a set the element order should not matter. So for some data structures like red-black trees, structural comparison is not possible. So that's why I like radix trees, because in them it is possible. So data structures that have a unique representation, there are actually some in the scalar collections. The very old scalar collection immutable long map and int map have this property because they are tree. The radix tree, obviously, and something as easy as simple as sorted lists also have the property, provided that the ordering is total. And collections which don't have a unique representation, which are called history dependent, we've seen the red-black tree, and very unfortunately also the hash set and hash map have this property that the structure is not unique, which is only because of the collisions. When there is a hash code collision, the items are stored in a list in whatever order they came first. So if it wasn't for collisions, if you have a hash tree, like a hash map or hash set without hash collisions, then the structure is actually has a unique representation. So, yeah. I don't want to dwell on that too much. So one nice thing I kind of discovered when I wrote this tree is that I spent a lot of time making the in-memory representation as compact as possible, like the ability to use arrays directly and making sure that I'm not using any scalar collections inside, which add a lot of tiny little objects. And I thought, can I do more about that? As we have seen, the German language has lots of redundancy, so you often have common suffixes in words, so the last letters. And the radix tree data structure itself automatically eliminates common prefixes. But it turns out we can also do something about common suffixes, which is, and another thing is common, like internal prefixes, so basically any kind of internal fragments. The way that works, I have a very constructed example. These are the numbers 22, 31, and so on. So basically numbers which have a very, very regular structure written as words. And as you can see, if you look at this tree, you see that there's lots of commonality. For example, here we got a node with the value 1. This is not a string, but a node. And here we got the same thing again. Again, for 2, we also got here 2 and here 2. And now, if I would go over this tree and take all nodes which are identical to nodes I've already seen and replace them by the original copy, so basically just remove all redundancy, I end up with this. So as you can see, the tree, the root and the rest is still the same, but at the leaves, I basically reuse nodes. 1 I'm using 3 times, 41, 31, 21. So in this example, I save a little bit, but I'm going to show an example with real-world data where you can see that this actually makes a big difference. So there are the two trees side by side. Again, you see that this is not that much smaller than the other one, but again, it's a very, very small example. So for some real-world test data, by the way, this is the implementation of the method. It requires a hashing for the value, because the values are also interned, not just nodes. And it requires a key which contains a hashing. So basically, this allows you to figure out if two nodes are identical. Without the hashing, you wouldn't be able to do it. So typical usage pattern is you build a big tree, then you pack it, and then you use it for a long time. So I can't afford to call that every single time I add an element because it would be very slow. So let's take a look at the benefit with real-world data. There's a nice tool that allows you to measure how much data structures actually consume in Java virtual machine memory, which is called JAM. And I use that kind of in my project to make sure that my assumption about how big things are actually correct. And here's what you get. English words, this is a small dictionary of English words. This is the size of all the strings concatenated. This is the size of the radix tree, and this is the packed size. And there's improvement of a factor of 5, which is not bad. So the thing is actually smaller than just the list of strings concatenated by quite a significant margin. But now let's take a look at German words. German words have much more redundancy. So I have a very large corpus of German words with lots of inflections also in there. And if I create a radix tree, it's slightly bigger than the flat list of strings because of all the nodes. But then when I pack it, I get a factor of 7.7 improvement. So this might actually be useful if you have a large dictionary of strings and you want to check against them and you want to make sure that it fits into your heap, then you might be able to use this. I mean, it's a huge difference if your data structure is like 184 megabytes or 23 megabytes in memory, regarding cache and also regarding total heap size and so on. So this is a numbers, basically just numbers text, and there the benefit is extreme, but this is a very regular data set, so it's not surprising. So the packing benefit increases with the verbosity of the data set. So now imagine the efficiency for a dictionary of Java identifiers, like this, or this. This would be off the scale. So actually, maybe you should build this into a Java compiler. There's a nice project here that allows you to generate these enterprise class names. I found it quite funny. So now the packing implementation basically just goes through the tree and then has a memo, is a dictionary of things that it's already seen, and just packs all the keys, so the prefixes, all the values, and also nodes itself. So if it sees a node that is exactly identical to a node that it has seen before, then it just keeps one copy. I don't want to go into much detail here because I don't have that much time. So yeah, there are some operations which simplify implementing type classes. There's a merge operation that allows you to pass a function to specify what to do in case of a collision, and that you can use to implement an additive monoid very easily. I mean, it's all boilerplate. The only interesting thing is here, the merge with call. Okay, so now I think I'm basically done with presenting the data structure itself. So in summary, it's a very small focused library that I just needed for myself. And I just put it on GitHub, obviously, because it has to be somewhere. And I put it on Maven so I could pull it in as a dependency. Well, and then there was surprisingly quite some interest from other users. I mean, not huge, but certainly there were some people that needed this. And I thought, well, great that I put it in there on Maven, even though it is not very generic. Like I said, it's not a replacement, definitely not, for Scala collection immutable sorted map. For all benchmarks which I haven't shown, this is actually much slower than a sorted map. So it's not a general replacement. But for my case, it was very useful. It's useful if you need the fast ability to prepend prefix or filter by prefix, or if you want a compact representation, the ability to have a compact representation. So, and I would love to see more of these small raw data structure libraries seen published, not just somebody having it somewhere on his hard drive and playing around, but just publish it, even if it's not completely finished or if it's not comprehensive. So now I get a little bit opinionated and tell some in my humble opinion, things about how you should organize your data structure library if you want to base it on CATS type classes. So you should not attempt to re-implement Scala collections. Trust me, I know. And you should also probably not try to re-implement the STL, because life will interfere and then you will end up with a huge pile of unfinished stuff which is not usable to anybody. So it should be just one thing, but do that one thing well. And then at some point, if you had a huge ecosystem of lots of tiny libraries, you could take all these and wrap them up in a generic way as a collection library, in quotes. But the collection library would be just a choice of all the available libraries that do one thing. So, as an example of what's not very good today, so the Scala collection library, I mean, many people hate it, many people complain about it all the time, but it contains quite a few very nice data structures. There is a bitmap vector tree underlying vector. There is a tree, a binary tree underlying hashset and hashmap. And there's a good implementation of a red-black tree underlying treeset and treemap. But if you were to write a tree map, red-black tree, for example, you wouldn't be able to reach into Scala collections and use that. You can use the tree set, but you can't use it as a tree. You can just use it as a set. So the implementation of the actual data structure is hidden and not reusable. So actually you can use them as trees, but only if you do horrible hacks using reflection or using namespace tricks, which I'm doing in a library of mine called Persistent Summary, where you can basically do summaries on existing Scala collections which are persistent when you update them. But it's really, basically, I'm just like gripping into the bowels of the collections to do that. So it's really not the correct way to do, but it works. And also the library which we have seen, which is creating these beautiful visualizations of Scala collections libraries, of data structures, is also using this trick. This is called RefTree, and it's so much fun if you like data structures, because you can visualize all the data structures underlying Scala collections, and also your own. So another thing about Scala collections, which I don't like that much, it's really not obvious which methods are fast. So fast as in as fast as they can be given underlying data structure, which are slow, like index on a single linked list, or which don't terminate at all, like iterator from zero.length. So, I mean, it's unavoidable if you put it into a trait hierarchy, or maybe not, but I don't want to dwell on that point now. But if you just have your naked data structure, then you can only expose the stuff which is actually fast for that data structure, and then it will be immediately obvious if you have a linked list, there will be no index, because index on a linked list is slow, so you shouldn't do it. So wouldn't it be great if, so the algorithms and data structures of Scala collections were published as separate artifacts, and you could use them directly. And then you could also use them encapsulated in a trait hierarchy, like the current Scala collections. So, okay, let's assume that you agree with all that, and you actually want to publish your own little data structure library. I don't know, maybe sorted set based on array, something very simple. So the first thing you have to do if you want to use type classes, you have to decide which type classes to use. I'm using the CATS ecosystem, which is also the title of the talk. So here's a quick overview about how the CATS collections type classes are organized. There's a library called CATS kernel, which you usually don't see. But this is a dependency of CATS, and this contains the very, very, very basic type classes like EQ and order, which you're definitely going to need for most data structures. And then there's cats, obviously, which has lots of very complex higher order stuff, but also has show, which you also probably want to implement. And then there's algebra, which has some more algebraic data structures like additive monoid, ring, and field. And then, of course, depending on these libraries, there are some more focused libraries like Spire, which have some, let's say, esoteric type classes like vector space and trig. And this is, again, in my opinion, you should take this as your kind of standard library and say, these are the dependencies I can always have, because they kind of evolve at the same time. But if you want to have a provide type classes or support type classes from Spire, you would make that as a separate addition to your library. So which type class instances should you provide yourself? By provide, I mean you should just put them into your companion object. Definitely should provide EQ. You're definitely going to need it for your tests. And show. And in addition to that, you should not try to implement every single type class instance, because there's a lot of them. You should just provide what you can implement yourself, what you need yourself. So where you have a real need for it, you should provide it. Otherwise, just leave it out. And that's the next thing. You should keep your data structures accessible from the outside. So basically, the great thing about type classes is that they are not baked in, but they're external. So you can basically, your users, if they need one particular type class instance, they can just implement it based on your open data structure. So obviously, you still have to hide some things. So you have to hide if you do dirty things inside your data structure, like using null and using arrays and using mutability, you have to hide it. Because, yeah, that's just too much. Dependencies, as I said, you should try to depend on these three, and you should try to avoid big other dependencies if possible. One example from my library, there is a very nice value class option in Spire, which is called spire.util.opt. But in order to use it, I would have to add all of Spire as a dependency, which would have made the whole thing giant. So I basically just decided to copy the thing into my library, make it private, and then eliminate everything that I don't need. And actually, I don't need much of it, so it's just one file. So this is the way to go if you have a small dependency on a big library. So test coverage. Time's up, but I'll hurry up. So it's so easy to get good test coverage these days with discipline and so on that you should just go for 100% test coverage. Just leave out stuff which you can't test. Make it minimal, but have test coverage 100%. Because, well, first of all, you can eliminate that code. And next thing, if you publish a library, you should be able to take some pride in it and have some fun. And if somebody has a bug and you have to fix it at a time where you don't want to, then it's no longer fun. So if you have 100% test coverage, of course it doesn't protect you from bugs, but it gives you a certain level of peace of mind. So again, you should memory usage tests. If you make some assumptions about how your memory is organized, you should also test them. It doesn't have to be automated, it can be manual, and you just run it before you deploy. Performance tests is the same. You should probably write manual performance tests and then just validate your assumptions using that. And there's some great libraries for that. Time is for more like interactive testing, and JMH is for like the take it to the bank results, which you can definitely say this is how it will behave on the JVM. So general guidelines, no complete list, just do whatever you need. And if you want to have a bridge to Scala collections, just provide traversable. That's easy, and it gives people everything they need, and you don't have to like blow up your code to implement Scala collections interfaces. Okay. So again, you should probably not use mutability on the outside, but on the inside is perfectly fine, especially if you care about performance. And you should look for canonical representation. This is one thing, the last important thing maybe. It's better to have 95% of all use cases covered with good performance than to have 100% use cases covered with so-called asymptotically optimal performance, but with a horrible constant factor. Because, yeah, it doesn't matter if it has a good big O performance if it's slow. So, okay, I got some more here, but I'll keep it short. I think the basic things are yeah, this is yeah, sometimes it's not possible to implement hash code and equals in a proper way, and in that case you just do this. Basically just, no, I don't do that. If you want to compare things, use the EQ type class, and if you want to hash things, use the hashing type class. Yeah, I would love to have a hashing type class in the type level ecosystem, something simple like that. But okay, yeah, I think that's basically it. Here's a bunch of interesting libraries if you like trees. So yeah, that's it.